Hello everyone, I hope all of you are doing good, and today I am here with a video on class 7 science, motion and time. We are going to cover this entire lesson in two videos. The first video we deal with the theory and the concepts, and the second video is all about questions. So are we waiting for something? Not really. So let's get started with the first video. So motion, that's what we are going to talk about in this lesson. So what do we mean by motion? Literally, if you ask the literal meaning of motion, it is nothing but movement, moving from one place to another. So that's like in very simple terms, that's how we can define motion. But when it comes to physics, when it comes to science, how do we define motion? We say it is change of position with time. Now, that sounds a little more, scientific. So what does this mean? So let me take an example. So you take the example of the fan. When you switch on the fan, what happens? It makes you feel cool. Why does that happen? Because the blades of the fan are continuously moving. So if you look at this picture right now, what is the position? Let's number the blades. So this is blade number 1, this is blade number 2, this is 3, this is 4, and this is 5. These are the 5 blades of this fan. Now, when you switch it on, what happens? It starts moving. So just observe the position of blade 1 when it is at rest. So right now, this is the position. So it is here. But as soon as it starts moving, what happens? The same blade 1 is actually changing its position with time. So as time is passing by, the position is also changing. So then we say that the blades of the fan are in motion. That is, it is moving. So here we will take the example of a moving car. Now, when the car is at rest, so whether you assume it to be a toy car or you assume it to be a real car. So when the car is at rest, so what happens? It is at a particular position. For example, let us say that right now the car is at rest and this is the position of the car. So let's say this point is A. Okay, so it is at point A on the road and it is not moving. But what happens when it starts moving? Now when this car starts moving, its position changes. So initially it was here and now it is somewhere here. So let us call this as position B. So the position of the car changed from A to B with time, because as time is passing by, so with every second passing by, the position of the car is moving. So first it was at A, then it was at certain point of time it was at this point, again at certain instant of time it was here, again at certain instant of time it was here. So as time is passing by, the position of the car is also changing. So what do we say? That the car is in motion. So let's look at a couple of other examples. So whenever we talk about motion, a motion is not always something which is related to objects. Even we move. So anything that is moving, anything which is undergoing a change in position with time is said to be in motion. For example, when we play, so while playing, you are running, so obviously you are in motion because your position is changing with time. Your hands are moving, your legs are moving. So obviously you are in motion. While running again, so what happens when you run? You move from one place to another, so your position changes with time. So you are in motion. Now let us take this example. When you are sitting on a chair and you are working on your laptop. Now in this case, your body might not be in motion because you are not changing your position from one place to another. But if you concentrate on your fingers, what happens? When you are working on your laptop, your fingers are moving. So the position of your fingers are changing with time. So your fingers are in motion. Think of a bird. So a bird flying from one place to another. So that is nothing but motion. Think of a lady dancing. So when you dance, again, you move your hands, you move your legs, you move your body. So everything is changing. All parts of your body, they are changing position with time. So again, you are said to be in motion. Okay, so these were some common examples of motion which we see around us. Now let's talk at a little more higher level. So let's talk about the motion of the earth. So the entire earth in itself is again in motion. So how the earth is moving? So let's have a look. So we all know that Earth is a planet, is one of the 9 planets, and all these 9 planets, they move around the sun. So this is the sun. In this picture, this is the sun and this is the Earth. Now sun is obviously bigger than the Earth, but here we are showing this picture like the Earth is nearer to us, so we are able to see it big, and the sun is quite far away. Okay, so now this Earth, it moves around the sun. So in that case, what happens? There is change in position of the Earth and with time, so the Earth is in motion, and also the Earth rotates around its own axis. So that means the Earth will rotate like this. So that ways each point on the Earth is also undergoing a change in position with time. So let us try to understand this even better. So basically, movement of the Earth around its own axis. So this is this blue line which you see, that represents the axis of the Earth. So movement of the Earth around its own axis, like this, like this. So this movement is called rotation, and movement of the Earth around the sun, that is called revolution. So that is, it is revolving around the sun. So these are the 2 different terms which are used for these 2 types of movements in Earth's context. So let's look at this animation. This will help you understand better. So let's say this is the Earth, okay, and this is the sun. So here what happens, the Earth moves around its axis, as you saw just now. So this type of movement, this is like moving around its axis, that is rotation of the Earth. So there also we see that each point on the Earth, so a point which was here, when it started moving, for example, when it started moving, so that particular point is also changing its position with time. So it is in motion. Again, the same Earth at the same time is also moving around the sun. So when it is moving around the sun, obviously its position is changing from one point to another with time. So both rotation and revolution of the Earth takes place simultaneously. So like as the Earth moves around the sun, at the same time it is also rotating around its own axis. So this shows that the Earth is also continuously in motion because its position is changing with time. So that is another classic example of motion. You talk about the motion of a spinning top. I am very sure all of you know what is a spinning top, and you would have played with it in your childhood, or maybe you play with it even now. So just look at this. This is a spinning top. So once you spin it, so it keeps moving on its own. So this is also an example of motion. So you see all these examples, they are all different types of motion. So in some places we see that the object is just moving on a straight path, for example a moving car. In certain cases we see that it is moving in a circular path, kind of circular path. For example, the motion of the Earth around the sun. Here in this case, we see that it moves around itself. It is moving around an axis and it keeps moving around itself. You think of a ball which is rolling down the slope. So if you look at this ball, what's happening? It is rolling down the slope. So the position of the ball is changing from one place to another. So that is motion. Even the rolling of the ball, when the ball is rolling, so one scenario could be the ball is just moving like this. The other scenario is the ball is rolling like this. So in case of rolling also, each and every point on the ball, it changes its position with time. So that means the ball is in motion. So these are all examples of motion. Another very important example of motion is the pendulum. So this is a classic example, and here we see again a different type of motion. Now have you ever observed the wall clock in your house? Now these days not all houses have this so these type of clocks were more common in the olden days. So where you see the a pendulum hanging here, and it keeps moving in a particular type, in a particular form. So this is how the pendulum moves. So you have a pendulum, a string kind of a thing, a very thin thread-like structure, and at the bottom you have a bigger mass, a ball-like structure. In fact, you can try to make a simple pendulum with a stone and a thread. You take a stone, tie it with a thread, and then hold the thread at this point. So you fix it at this point, and then just give it a little bit of push here, and then what happens? It keeps moving in this fashion. So this type of motion of the pendulum, so this is also a motion, right? Because if you look at the position is changing from here to here to here, again it is coming back here, again it is going here, right? So it is basically changing its position in a particular form. So what kind of position it is, like what kind of motion it is? Moving here, coming back, moving till here, and again coming back to this point. So this point is known as the mean position. So this is called the mean position, and these two positions are called the extreme positions. So these two are the extreme positions. So basically it moves from mean position towards one extreme position, again it goes to the other extreme position, again it comes back to the mean position, and then this motion is repeated over a period of time. So it is like a periodic motion because the entire motion gets repeated in periodic intervals of time, and this type of motion is known as oscillatory motion, and this is called oscillation. So what is one oscillation? So moving from here to here, coming back, and again coming back here. So this complete one cycle is termed as one oscillation. So that is called one oscillation. So oscillatory motion is periodic in nature. Why periodic? Because it repeats itself. So if you look at this motion, so this one oscillation, that means from here till here and again coming back to here, that is one oscillation. So this one oscillation, this motion keeps on repeating. So that is why it is called periodic motion, because it takes place in periodic intervals of time, and the time taken to complete one oscillation is known as time period. So time period is one very important parameter of a pendulum. So time period is the time taken to complete, or the time taken for one oscillation. So whatever time it takes to complete this one oscillation, that is known as the time period of a pendulum. So for a particular pendulum, the time period will remain constant because all the oscillations are going to be the same thing. So all the oscillations are actually repetition of each other. So the time taken by first oscillation would be equal to the time taken by the second oscillation, that will be equal to the time taken for the third oscillation, and so on. So therefore the time period of a particular pendulum will remain the same, and this time period depends on the length of pendulum. So what is the length of pendulum? That is the length of this thread of the pendulum. So it depends on this length of the pendulum. So you see, this is an interesting example of motion. So this was a special type of motion called oscillatory motion, and pendulum is the best example of oscillatory motion. Now when we talk about motion, we already looked at a couple of examples of motion where we saw that some objects move on a straight path, some objects move in circular path, some objects rotates about itself, but all of these are motion because there is a change in position with time. Now an interesting thing about motion is that motion is relative. What do we mean by relative? That means motion of an object is always with respect to some frame of reference. Now what is this frame of reference? Now whenever we talk about motion, it is always with respect to something else. For example, let us look at this example. Let's say that these people, they are standing at the bus stop waiting for a bus. Now there is a bus which just moves by. Okay. So what will you say? Is the bus moving? Yes, the bus is moving because the position of the bus is changing with time. So initially the bus was here and now the bus is here. So the bus is moving, of course. But the bus is moving with respect to these people who are standing at the bus stop because they can see it changing its position with time. Now, if you look at the same bus, now let's assume that you are not standing at the bus stop, rather you are sitting inside the bus. So you are inside the bus, let's say. Okay. Now, if you are inside the bus, do you see the bus changing its position with time? Not really. So for somebody who is sitting inside the bus is at rest. But for somebody who is outside the bus is in motion. So we are talking about the same object, but for one frame of reference, it is moving, but with respect to some other frame of reference, it is at motion. So this is what we mean by relative. So any object which is moving, it is moving for certain things and it is not moving for certain other things. And this is what we call as relative nature of motion. So that is why we say that motion is a relative term. So whenever we say that this particular object is in motion, that means it is in motion with respect to something. So now that we learned about motion, there are many different types of motion. I have already given you an example of oscillatory motion, the motion of the simple pendulum. So let's look at another very simple type of motion which is commonly experienced by us in our day-to-day life, and that is called rectilinear motion. So linear means something which is in a straight line. So motion along a straight line is known as rectilinear motion. So one example of rectilinear motion could be a car moving along a straight line, along a straight path. So this is an example of rectilinear motion. Now you see, different types of motion are so much different from each other. So rectilinear motion is like this, whereas when you talk about the oscillatory motion, which is nothing but a periodic to and fro motion, that is like this. Correct? So that is oscillatory motion. Now the question is, how do we describe the motion of an object? How do we describe that how exactly a particular object is moving? Because there are many different ways in which an object can move. Now, as I have mentioned before, that whenever we talk about motion, two important things are position and time. So these are the two most important things, and that is why you see both these parameters are included in the definition of motion. So in order to describe the motion, position needs to be defined. That is very, very important, because only when you know the position of an object, you will be able to judge if the position has changed with time or not. So position needs to be very clearly defined. And what is position? It is nothing but the point at which the object is located at a particular instant of time. So let's look at this example. You see this little boy on the cycle? So right now the boy is at rest. So let's say the boy is located at this particular, so location is this one, and at a particular instant of time. Now when he starts moving, so he starts cycling, what happens? As he keeps moving from this position A, its position keeps changing. So at certain time it was here, then here, then here, and finally it has reached this position. Let's call this position B, and the time has also passed by during this period. So that means the time also changed and the position or the location of the object also changed. So this location is termed as position. So now in this case, we could clearly say that motion had taken place because there is a change in position. And how do we know there is a change in position? Because we had defined the initial position, and therefore we can determine if the final position is same as the initial position or final position is different than the initial position. So knowing the position is very, very important. Now, when we talk about motion, another important, we are actually talking about movements, or we are talking about position changes. So when it comes to movements, something which is very commonly being used in our day-to-day life is fast and slow. So how do we know which object is moving fast and which object is moving slow? So how exactly do we define that, or how exactly do we determine that? What determines the speed of motion? So that is where we introduce speed. So we will talk about speed a little later, but in this picture, what do you see? You observe that the blue car was fast and the red car was slow. So why was this an example of fast motion? Because it very quickly changed its position. So in a short interval of time, it reached from position A to position B. But the red car, it took more time to reach from position A to position B. So basically, how much time it takes by a particular object to cover a particular distance. will define whether that object is undergoing fast motion or slow motion. So that is where comes the concept of fast and slow. So let's look at this. How do we determine that which is faster? The distance moved by objects in a given interval of time decides which one is faster or slower. So let's look at this example. So you have a bike and you have a bicycle. So these are the two vehicles that you have. So now if you want to compare which of these two is faster, so let's try to compare these two vehicles. Now let's say that we fix a time interval. So let's say we fix a time interval of 5 minutes. And then we just observe how much distance is covered by this bike and how much distance is covered by this bicycle. Now what we see is that in 5 minutes this bike could cover a distance of around, we'll just take examples. Let's say it covered a distance of 3 kilometers, and in the same duration of 5 minutes this bicycle could cover a distance of 2 kilometers. Okay? So which one is faster? No, the time interval is the same. So in the same time the bike covered more distance when compared to the cycle. So that means the bike is faster. So the bike is traveling fast. That is why it could cover more distance in the same time when compared to the bicycle. So this is how we can determine which one is faster. So fast or slow is actually defined by the rate of change of position with time. That is how fast the position is changing with time. Because when we were talking about motion, we were only talking about the change in position with time. But when we talk about the fast or slow speed of a vehicle, we are actually talking about the rate at which the position is changing with time. How fast or how slow the position changes with time. So that is how we can say that the bike is faster and the bicycle is slower. So this is where we introduce the term speed. So when we talk about fastness or slowness of motion, we have to introduce speed. So what is speed? It is the rate at which an object covers distance. That means how fast or how slow, how quickly or how slowly an object is able to cover distance with time. So speed is a scalar quantity. What is a scalar quantity? It is such a quantity which only needs magnitude for its definition. That is just a value. So we say the speed of a vehicle is 5 meters per second. So that's the speed. So we do not need any direction. So these type of quantities are called scalar quantities. You will learn more about scalar and vector quantities in your higher classes. So let's look at an example to understand speed even better. So as I said, speed is nothing but the distance covered divided by the time taken. So this is how we calculate speed of an object. So let us take the example of this car. So if we say that this car travels 50 kilometers in 1 hour. So let us say that it travels 50 kilometers in 1 hour. So what would be the speed of the car? So the speed of the car is actually distance traveled, which is 50 kilometer divided by time taken, which is 1 hour. So basically the speed of the car would be 50 kilometers per hour. So that is how we define speed. Now any object which has a higher speed moves faster because it is traveling more distance over a specific period of time. Any object which has a lesser value of speed is traveling at a slow speed. So it has a slow motion. So that's about speed. So let us look at more examples of speed. So let's look at this example where this little boy is trying to travel from his home to the McDonald's. So this boy is on the bicycle. So now this little boy is moving, or he is traveling from his home to the McDonald's, and his travel time is 10 minutes. So it takes him 10 minutes to go from his house to the McDonald's, and the distance between his house and the McDonald's is 2 kilometers. So the McDonald's is 2 kilometers away from his house. So if I ask you to calculate the speed with which the boy is moving, how will you do that? So the speed is nothing but the distance which he traveled, which is nothing but 2 kilometers, divided by the time which he took, that is nothing but 10 minutes. So if you convert minutes to seconds, so it was going to be 10 by 60 hour. So this is going to be 12 kilometers per hour. So this is the speed with which the boy was moving when he traveled from his home to the McDonald's. So this defines, that means it now, what does this 12 kilometer per hour means? Now literally it means that the boy traveled in 1 hour 12 kilometers, but actually he traveled only 2 kilometers. But speed tells us that, okay, this is the rate at which he moved. So had he traveled for 1 hour, he could have covered 12 kilometers. So it just gives you the rate, it just gives you the distance which the person could have covered in 1 hour or in 1 second or in 1 minute. So with respect to whatever unit of time you are referring to. So that is how we calculate speed. Now similarly, let's say that the boy also comes back from the McDonald's. So let's say we take another example where the boy goes to the McDonald's, like he travels from his house to the McDonald's and then immediately he comes back from McDonald's to his house. And we say that what would be the total distance? Now let's say the total distance of going and coming back would be 4 kilometers. Correct? And let's say that the total time that he took was, say, 30 minutes. Now we are assuming that he didn't get down at McDonald's at all. He just went there, but as soon as he reached McDonald's, he changed his mind and he started coming back to home. So if we say that the time he took was 30 minutes, in that case, what would be the overall speed? So again, you can calculate it in a similar way, distance traveled by time taken. So I'm leaving that as an exercise to you. So I hope it is clear that how do we calculate speed and what is speed all about? What does speed tell us? It just tells us the distance that a particular object can cover in unit time, whether it is in 1 hour or in 1 second or in 1 minute. So now that we spoke so much about motion, I think the basic concept of motion is getting clearer to you. So now we will see how do we graphically represent motion. This is going to be interesting and this is also going to be new. Now before we talk about graphical representation, what do we mean by graphical representation? What are graphs? Now have you ever seen a graph while going through a newspaper or over the internet? So graphs are nothing but pictorial representation of data. So let us take an example. Let us say that the teacher in your class, she asked the students which is their favorite fruit. Now there are several fruits available. Some students like apple, some like oranges, some like grapes, some of them like banana. So different students have different choices. So now there are so many students in the class. So let's say there are almost 100 students in the class. Now some said apple, some said orange, some said banana. Now it is very difficult to represent this data. So how to represent this data? So graph is a pictorial representation, or it is a diagram that shows relationship between two different quantities. So what are the two quantities in this case? The number of students in the class, that is how many students said they like apple, how many students said that they like grapes, how many said that they like mango. So basically number of students is one variable and the other quantity is the fruit, because some like orange, some like apple, some like banana. So with the help of these two quantities, that is the number of students and the fruits. So taking these two on two different axes, we have plotted a graph. So now with this graph, you can very easily determine how many like apple. So here you can see that 50 students like apple. Again you see mango, around 40 students like mango, 30 students like grapes and 20 students like banana. So with this graphical representation, it become easier to indicate or to display this entire data. Otherwise what you could have done is, now as I said, that's now since there are hundreds of students, more than 100 students in the class, then for each student you will write, okay, this person likes apple, this person likes banana, again this person likes apple, this person likes grapes, and so on. So to make the representation clearer and easier, graphical representation is often used, and this is known as a graph. So what you see on the screen is nothing but a graph. Now you would have seen these kind of graphical representation in the newspapers also. In a newspaper, you would have often seen that the weather reports often have graphs showing how the weather changed in the past couple of days, how the temperature changed in the past couple of days or in the last month, or how the temperature is changing in different cities. So you also would have seen graphs in the stock market news where it says that how the price would have decreased or increased in the last few days or last few years. So graphs are something which are very commonly seen in the newspapers as well. So if you want, you can actually scan through your newspapers and see where you can get a graph. Now the question is, what is a graph? So it is a diagram that shows relation between variable quantities. Now what are variable quantities? That is quantities which do not remain constant, that is they keep changing their values. So in the previous example, I took the example of the number of students and fruits. So the number of students also changed, like for apple it was 50, for banana it was 20, so it changed, so it was a variable quantity. Similarly, the fruits also changed. Somebody likes apple, somebody likes banana, and so on. So and those two variable quantities, there was a relation between the two, and which was shown by the graph. So here let us take another example of a car. So let us say when this car moves, what happens? As the car is moving, its position is changing. Therefore, the distance covered is also changing. So when the car was here, it had covered no distance. When the car reached here, it had covered this much distance. Now the car is here, so it has covered this much distance. So as the car is moving, so the distance moved is also changing, and the time is also changing. Maybe when it was here, it was only, say, it only took 5 seconds. By the time it reached here, it took maybe 30 seconds. Again, as it moves forwards, the time also changes. So basically, during its motion, at every point, the time was also changing. Correct? So let us try to plot this motion of the car in a graph. So how will we do that? So let us say this is the start point. So this was the start point of the car, and let us say this is the end point. Okay. Okay. So now let us assume that this car had reached a point here. So when it reached a point here, it had traveled 1 kilometer. So the distance that it had traveled is 1 kilometer, and it took 10 minutes for the car to reach here. Now the car didn't stop here. I'm just taking certain instance of time. Again, when the car was somewhere around this point, okay, so when it was here, so let's name these points. This is A, B. So by the time it reached point B, so it had traveled another 2 kilometers. So from A to B was 2 kilometers, and the time which it took was, let's say, around 30 minutes. So I'm just taking some random values. And let's say that again from B to the last point where it finally went, so let's say this distance was another 1 kilometer from B to the last point. And how much time it took to travel this much distance? It was, say, 5 minutes. Okay, so this is how it moved. So sometimes it was moving slow, sometimes it was moving fast, and that's how it reached from the start point to the end point. Now, if we want to plot it through a graph, what we have to do? We have to plot a graph like this. So this point is termed as the origin, and this is the x-axis, and this is the y-axis. So ideally, we always take time along the x-axis, and we take distance along the y-axis. So that is the convention that is followed. So let's say here also we are taking time along x-axis and distance along y-axis. So now the time, as you can see here, let's represent the time in this way, and this time is in minutes. So 10, 20, 30, 40, 50. And on the y-axis we are representing distance. So let us say it is 1, 2, 3, 4, and so on, and the distance is in kilometers. So what do you see? Initially, the car travels, when it reaches point A, it travels 1 kilometer in 10 minutes. So 1 kilometer is here and 10 minutes is here. So basically this point. After that, it traveled 2 more kilometers. So basically how much total distance it had traveled by the time it reached B? It has traveled 2 plus 1, that is 3 kilometers. Total 3 kilometers it traveled in how much time? In a total time of 40 minutes, right? Because here we are actually measuring these values from 0, correct? But here we are measuring the value from point A. So therefore, it is 2 kilometers in 30 minutes. You should not mark it as 2 and 30. So that will become incorrect. Because from the starting point, how much distance is had traveled till B? The total distance is 3 kilometers. So this is 3 kilometers. And how much time? Time is total 40 minutes. So this is here. So that next point would be here. And finally, when it reaches, it had traveled how many kilometers? Total 4 kilometers, the entire distance, and the total time taken was 45. So 4 kilometers and 45, somewhere here. So, and then you join all these points, something like this. And this denotes, this is known as the distance time graph. So when you look at this graph tells you that how the particular car was moving. So at this much point, this was its speed. At this point, it traveled this much distance. So this is how a distance time graph looks like. And this is a graph. So here we are going to talk more about the graphical representation. We will see that what are the information that are like given by a distance time graph. Now there are many types of graphs that exist. So as you can see in the picture itself, there are so many different shapes of graphs. Some of the common types of graphs are bar graph, line graph, and pie charts. So as you can see on the screen, each of these graphs, they look very much different from each other, and all of them have different way of representing the data. So in the previous slide, I took an example of the graph which was actually a bar graph, because you see bars like this representing numbers. Similarly, when you look at a pie chart, it is like it is in a circular form where we divide it into segments, and each of these sectors, they represent a specific amount of data. So here you can see this is also a pie chart where you have blue, orange, green. So each of these colors, each of these parts, they represent a specific set of numbers. In case of line graph, instead of bars, you have lines like this where the peaks and the troughs, they actually represent the numbers again. So these are all various ways of representation. So let us look at the representation using different types of graphs. So we have taken the same example of the favorite fruits of the students of class 7. Let's say, so here you see this was the graph. This was the bar graph which I had discussed in the previous slide. So in the bar graph, we saw that 50 students like apple, 40 of them like mango, 30 of them like grapes, and 20 of them like banana. So the same thing can be represented using a pie chart. So you see here, this is how a pie chart looks like. So here this is the pie chart. So for banana, it is like a smaller section, the red colored section. For grapes, it is a bigger section. For mango, it is even bigger. And for apple, it is maximum, because in apple, you have almost 50 people. Similarly, in mango, you have around 40. In grapes, you have around 30. And for banana, you have just 20. Now the same data can be represented using a line graph as well. So here you see, the entire plot is done in a similar way as bar graph. Instead of the bars, you just plot the points and then you join the points to form a line graph. So this is how a line graph would look like. So that's how we represent the same data using different types of graphs. So in this lesson, we will mostly, now when we talk about the distance time graph, because distance time graph is used to describe motion of an object graphically. So we are going to talk about the distance time graph, and in distance time graph, we will make use of the line graphs. Now, before we get into that, let us try to draw a graph ourselves. So we will take the same example of the car, because this would help you to understand the basics of drawing a graph in a better way. So let's say we have a car, and this car is traveling and it covers certain distances over the period of time. So let us say this car, so let's say we take time and we take the distance covered in kilometers. Okay, now let us say that this car, it in 5 minutes, okay, now this time is in minutes, so in 5 minutes it covered 2 kilometers, in 10 minutes it covered 4 kilometers, in 20 minutes it covered 8 kilometers, and in 30 minutes it covered 12 kilometers. So this is how, these are the numbers which define the motion of this car. That is how exactly the car is moving. That is defined by these numbers. Now, how best can I represent these numbers using a graph? So, in order to describe the motion of this car, which are the two variable quantities? So, one variable quantity is distance, the other variable quantity is time. So therefore, first of all, I will plot the x-axis and the y-axis. So this is the x-axis and this is the y-axis. So the vertical axis is the y-axis, the horizontal one is the x-axis, and this common point is called the origin. And at origin, the value of x-axis is also 0 and the value of y-axis is also 0. So this point is termed as the origin. So all the distances, all the measurements are done from the origin. Okay, fine. So now we take distance on the y-axis. So we take distance on the y-axis and we take time on the x-axis. So that's how we draw the backbone of a graph. Now the next important thing that we need to do is we need to decide the scale on the x-axis and the y-axis. Okay, so x-axis is all about time, and what are the time that we have? 5 minutes, 10 minutes, 20 minutes, 30 minutes. Okay, now how do we plot them? So let's say now if you actually look at a graph paper, if you have ever drawn a graph on a graph paper, you will see that the graph paper contains squares like this, and inside the big squares you have small squares like this. So that is how a graph paper looks like. So while scaling the x-axis and the y-axis, we assume that okay, one big box would represent these many units. Now why do we do that? I'll tell you about that also. So right now let us say that we assumed that one big box is representing say 5 minutes. So I say this is 5, this is 10, this is 15, this is 20, this is 25, this is 30 and so on. So let us say one big box is 5 units, or one big box represent 5 minutes. So that's how we scaled the x-axis. Now let us try to scale the y-axis. Now in the y-axis we have distance, and here the distance values are 2, 4, 8 and 12 kilometers. Now here I will tell you why do we need to do this kind of scaling on the x and y axis. Now do you think that it is possible to plot a distance of 10 kilometers on a piece of paper? A piece of paper is too small to actually measure 10 kilometers. 10 kilometers is a huge length. So how do we plot it on a piece of paper? So for that purpose we do this scaling. So we assume that, let's say that one big box represents 2 kilometers. So we just assume that. Okay, so one big box is 2 kilometers. So the next one is 4, 6, 8, 10, 12 and so on. So that is how we scale the y-axis. So now that the x and the y-axis have been scaled, now your job has become very easy. So now you just look at these numbers. So in 5 minutes it had traveled 2 kilometers. So 5 minutes, 2 kilometers. So this is the point. In 10 minutes it traveled 4 kilometers. So 10 minutes, 4 kilometers. In 20 minutes it traveled 8 kilometers. So 20 minutes it traveled 8 kilometers, right? And in 30 minutes it traveled 12 kilometers. So somewhere here, so this is 12 kilometers. Now you got these 4 points from the data that is given about the motion of the car. So now when you join all of these points, so when you join all of these points, you get a straight line like this. And this represents the distance time graph for the motion of this car. Now looking at this distance time graph, now since the distance time graph is a straight line which is passing through the origin, it says that it is a motion where the car is covering equal distances, certain distances in equal intervals of time. Now what all can we interpret from distance time graph, that we are going to discuss in the next section. But for now you should know how to plot a distance time graph. So I hope you understood that why do we do these kind of scaling, why do we assume that one big box represents these many units, right? So in this case, if you look at the x-axis, one big box is representing 5 units. Similarly, if you look at the y-axis, one big box is representing 2 units. Right? So that's how we plot or we draw a graph. So now that we got a good idea about graphs and how do we draw graphs, how do we represent data in graphs, so let us now talk in detail about the distance time graphs, because these distance time graphs are going to give us a lot of information about motion of various objects. So let's look at this example where we see this little boy is traveling from his home to McDonald's and then he is coming back from McDonald's to home. So when we try to represent it in a distance time graph where we take time on the x-axis and distance on the y-axis. Now the shape of the graph tells us a lot of things. Let's say if the graph is a straight line. So what does this graph tell? This graph tells that the object travels. Now let's say if say the time is in hours and let's say the distance is in kilometers. So this tells us that the object travel, any point on this line tells us the distance traveled in a particular time. So let's say we take this point. So this point on the graph tells us that in 2 hours, so this is 2 hours, this object traveled 2 kilometers, right? So that is what it tells us. So this point. Similarly, if you take this point, so this point tells us, so you join these points. So this point tells us that this is 3.5. So in 3.5 hours, the object traveled 3.5 kilometers. So any point on the line actually gives you information about the distance traveled in a particular duration of time. So that is something which you can infer from the graph. So looking at the graph, you can also tell what kind of motion the object has, whether the object is moving uniformly or the object is not moving uniformly. So all those information can also be derived looking at the distance time graph. Now some of the interpretation from a distance time graph are, the first interpretation is distance traveled at specific intervals of time. So that means any point of the graph will tell you how much distance is being traveled at a particular instant of time, as I was telling you. So at this point you can tell that it traveled 1 kilometer in 1 hour. At this point you can tell that it traveled 2 kilometers in 2 hours and so on. So you can actually tell how much distance has been traveled at specific intervals of time. So if I just give you this graph and if I tell you that how much distance has been covered in say a time duration of 3 hours. So this is 3 hours. So this is 3 hours. So corresponding to 3 hours, this is the point. So for this point, what is the corresponding distance? That is 3 kilometers. So you would say that 3 kilometers is traveled in 3 hours. So each point represents how much distance traveled in how much time. So with that information, we can actually tell us that when the car is moving, how much it has covered in how much time. Now, the second interpretation from a graph could be the distance traveled at a particular instant of time. Let's say if you talk about, so one thing is how much it traveled in 2 hours, right? So that is one thing. The another thing is how much it traveled at say the third hour, at the second hour. So if I tell you that how much distance it had traveled at a specific instant, at this instant of time, how much distance it had traveled. So you can very easily calculate corresponding to this how much distance has been traveled. Another thing is, if I tell you how much distance did it travel between 2 and 3 hours. So between these two, how much distance it had traveled. So for corresponding to 2, let's say it has traveled this much distance. Corresponding to 3, let's say it has traveled 3 kilometers. So that means basically in this much time duration, it has traveled this much distance, that is 1 kilometer. So basically it has traveled 1 kilometer between the second and the third hour. So all these calculations can also be done looking at the graph. So these calculations become easier. It also tells us about the speed of the vehicle, and this is very interesting. That is how fast the object is moving from one place to another. And how do we find that? Looking at the graph. So graphically, now normally what do we know? That speed is nothing but distance traveled per unit time. So that is how we define speed, right? But how do we calculate speed looking at the graph? Now the slope of this line tells us the speed of the vehicle. Now what is slope? Slope is nothing but the steepness of this line, how steep the line is. So this line could have been something like this. The line could also have been something like this. The line could also have been something like this. So how much slant the line is, that decides the speed of the vehicle. So that's the beauty of this distance time graph. So let's see, what do I mean by that? So let's stick to the previous line, that is the blue colored line. So in this line, let us say you assume any particular point, you consider any point. Let's say I have considered this point and I say that I want to find out the speed at this point. So what would be the speed at this point? So at this point, how much is the distance traveled? So the distance traveled is 2 kilometers. For this point, how much is the time taken? The time taken is 2 hours. So what would be the speed at point P? It would be distance traveled divided by time taken. So this is going to be 1 kilometer per hour. So that would be the speed at point P. So how did we calculate? That is the y-axis divided by the x-axis. And what is slope? Now what did I mean by slope? Slope is nothing but the slant of this line, and slope is given by this divided by this, that is slope. So basically this is nothing but the distance traveled and this is nothing but the time taken. Correct? So that is slope. So slope is something like this, slope of a line. So slope would be like this. Let's say this is a straight line. So the slope of, if I ask you what is the slope of this line? So the slope of this line is going to be this divided by this. So that would be the slope of the line. So if this is A, this is B and this is O, then slope is going to be AB by OB. So that is how we define slope. Now if this line is more steep, for example in this case, so let's assume this case. So in this case the slope would be something like this distance divided by this distance. So in this case you see the numerator is more, therefore the value of the slope in this case would be more. Correct? So let's say the slope for this is S1, slope for this is S2. So we will say that S2 will be greater than S1. But if you consider the slope of this line, so this would be this divided by this. Correct? So if you calculate the slope of this line, so this would come out to be less. So this slope would be less than S1. So if you want, you can actually try calculating this and then you can see that yes, that is how it is. So as the line becomes more and more steep, the slope increases, and slope of the line is nothing but the speed of the vehicle. So that's how, looking at the distance time graph, we can also calculate the speed of the vehicle. So now that we have got a good idea about motion, let us talk about these two types of motion, uniform and non-uniform motion. So what is uniform motion? Uniform means something which happens smoothly, something which happens smoothly, something which happens, like very regularly. So that is uniform. So a body is said to be in uniform motion if it covers equal distances in equal intervals of time. So what it means is, let's say this is a car, and this car is moving uniformly. So if I say uniformly, that means for every interval of time it is covering the same distance. That is, for example, it started from point A and it reached point B, right? So that's how the car moved here. Now what I mean to say is, let's suppose that in the first time interval, say in a time period of 1 minute, it covered a distance of, say, let's say 500 meters. In the next 1 minute, it again covers 500 meter. Again, in the next 1 minute, it covers 500 meter. So if it covers same distance in an equal interval of time, then we say that the motion is uniform. Whereas when we talk about non-uniform motion, that means it covers unequal distances in equal intervals of time. So as you can see in this picture, so here you have different vehicles. So all of these are moving with different speeds. So sometimes it covers more distances, sometimes it covers less distances. So as you can see here, the orange colored car, so it initially was like moving very slowly. So just look at this. Look at the green car and the red car. They are like moving gradually. So they are moving at the same speed. But if you look at the orange car, what do you observe? You observe that initially the car is moving slow and then suddenly it starts moving fast. So that means it is not covering equal distances in equal intervals of time. So this tells you the difference between uniform and non-uniform motion. So in case of non-uniform motion, maybe in the first, say, 1 minute, it travels 200 meters. It can happen that in the next 1 minute, it travels 500 meter. Again, it might happen that in the next 1 minute, it travels 10 meters. So this is an example of non-uniform motion. Now, looking at the distance time graphs, you can interpret a lot of things. Now that you know what is uniform motion, what is non-uniform motion, so we know a lot of things. So let us look at different distance time graphs and let's see what kind of information do we get from them. So let's say this is the distance on the y-axis, this is time on the x-axis. So if you have a graph like this, what does this mean? So this is the line of the graph. That means the time is increasing. As time increases, the distance covered remains the same. So that means the object is not covering any distance with time. That means the object is not moving at all. The object is located at the same position. So that is why the distance covered is same. It is at 3. So even though the time is increasing. So this would mean that the body is at rest. So the body is not moving. Body is not in motion. So looking at the graph itself, we could interpret that the body is not moving. Let's look at another case. So here you see a different graph. So here you have a graph like this where you see the time is increasing. So each point on the graph, if you try to look at each of these points, they will correspond to a point on the x-axis and a point on the y-axis. And as time is increasing, as the value of time is increasing from 1 to 2, from 2 to 3, similarly the distance covered is also increasing from 1 to 2 and 2 to 3. So as time is increasing, distance is also increasing in this case. And also here you see that in the first interval of time, that is in 1 unit of time. So if we say that this is an hour, so in the first 1 hour it traveled 1 kilometer. In the second 1 hour it traveled again 1 kilometer. In the third 1 hour it traveled again 1 kilometer. So it is covering equal distances in equal intervals of time. So that means the body is in uniform motion. So just looking at the graph, we could say that the body is in uniform motion. So I hope you understood this. So this is the first 1 hour. This is the second 1 hour. So how much distance is traveled in this second 1 hour? So how will you calculate that? So till 2 hours, the total distance traveled is 2 kilometer. But in the first 1 hour, 1 kilometer is traveled. So 2 minus 1, 1. So 1 kilometer is traveled in the second interval, and so on. Let's look at case 3. Here we have a graph which is similar to the case 2, but here it is not passing through the origin. So what does that show? That shows that initially the graph is like this. So that means initially, as time was increasing, the distance was not increasing, and only after that distance started increasing. So initially the object was at rest. So this portion till this much time, the object was at rest, and only after this the object started moving, and when it started moving uniformly. So whenever you have a straight line like this, it shows uniform motion. But initially the object was at rest. Case 4. So here you have a curvy line. So it shows that yes, if you consider any point on the curve, you see that time is increasing at each of these points. So as time is increasing, what do you see? The distance is also increasing, which shows that the body is moving, of course, but it is not moving uniformly. So in the first 1 hour, it traveled this much distance. In the second 1 hour, how much distance it traveled? It traveled this much distance, which is more. In the third 1 hour, that is maybe here. So you see again, it traveled less. So the distance traveled in each interval of time is different. So this graph portrays non-uniform motion. So therefore, whenever an object is in uniform motion, the graph would be a straight line. If the graph is a curved line, that means it is non-uniform motion. So now that we have spoken so much about speeds, how do you think we measure speed? How do we say we talk about the speed when we want to determine which object is moving fast and which object is moving slow? So how do we measure it? So speed is dependent on two main quantities. One is distance and the other one is time. Now we all know how do we define speed. So speed is defined as distance traveled per unit time. Now how do we measure distance? Distance is measured in unit. Distance measures length. So distance is measured in units like meters, kilometers. So these are the units to measure distance. Now how do we measure time? Time is primarily measured in three major units: hour, minute and seconds. Now, in order to understand these three, the best example would be looking at your wall clock. So on the wall clock, you can see a big hand, a small hand and a very thin and tiny hand which moves very fast. So these three hands will tell you the hour hand, minute hand and the second hand. So the smaller hand is the hour hand, the bigger hand or the larger hand is the minute hand, and a very thin hand which moves very fast, that is the second hand. Now the second hand moves with each second. The hour hand moves every hour. So from 2 it moves to 3 only after 1 hour. And the minute hand moves every minute. So that's how the three hands of the clock moves. And there exists a relationship between these three units of time. Now 1 hour is equal to 60 minutes. And 1 minute is equal to 60 seconds, right? So now these are the three possible units of time. So therefore, the commonly used units of speed are kilometer per hour or meter per second. These are the most commonly used units of speed, and we can interconvert the units. Like we can convert meter per second to kilometer per hour. We can also convert kilometer per hour to meter per second. So let us look at some examples. So let us say you have a value 10 meter per second and you want to convert it into kilometer per hour. So how do you do that? So 10 meter per second basically means 10 meter divided by 1 second. So how do you convert 10 meter into kilometer? 10 into 10 to the power minus 3 kilometer. And 1 second would be 1 by 60 into 60 hours. So when you calculate this, it comes out to be 36 kilometers per hour. So basically 10 meter per second is equal to 36 kilometer per hour. So that's how we, these are the common units of speed. And you would have seen these units written on the meter present inside your car or your bike. So have you ever seen the meter which is present inside your vehicle, which shows the speed of your vehicle? So as you start driving fast, so this hand, it keeps moving very fast. So, and at the end of it, you will see somewhere it would be written kilometer per hour or meter per hour, something like that would be written there. So this is how we measure speed. Now, when it comes to measuring speed, so unit is something which is needed for measuring speed. Besides that, there are certain devices also which are used for measuring speed. So these kind of devices are very evidently seen in the vehicle, especially if you get time, just try to observe it in motorcycles or bikes or cars, and you will be able to see these kind of devices. So the device is called speedometer. So speedometer is a device that measures speed. Of course, the name speaks for itself, speedometer, obviously measuring speed. Now similarly, there is another device called odometer, and it measures the total distance that is being covered till now. So inside the car, you have 2 meters like this. So one of these will measure the speed, as you can see here, per hour. So meters per hour, kilometers per hour, that would measure the speed, and this is the odometer, which will measure the total distance. So here you have the values like 1, 2, 3, 4 and 5, but wherever this hand indicates, that gets multiplied by 1000 to give you the total distance covered. So that's the difference between speedometer and odometer. So you would have seen that often people driving cars or people who want to sell their old cars, they often talk about how much is the total distance that is being driven by your old car. So how do you get that value? Through the odometer, because it tells the total distance that is being traveled by that vehicle. So that's the purpose of odometer. And speedometer, as you accelerate the vehicle, as you increase the speed, you can see the speedometer also running very fast. So that's about the devices which help us to measure speed. Now, when we talk about speed, it is not only the vehicles which we can think of when we talk about speed. You talk of animals, for example, cheetah, which is very much known for its speed. It is one of the fastest land animals, and it has a speed of around 112 kilometers per hour. So that's a huge speed. It runs that fast. You talk about human beings. Normally, human beings have an average speed of 40 kilometers per hour. You talk about wind. So wind also has a speed, the wind speed. Now, if you would have seen in the weather forecast reports, it often talks about wind, and it says 5 mph, that is 5 meters per hour. So similarly, you can see here, this line indicates the wind speed over a week. So every day the wind speed is changing. Sometimes it is 2, sometimes it has increased to 4, again it has decreased to 2, and so on. So wind speed also matters to, also influences a lot of stuffs. You talk about the moving blades of the fan, so that also has a speed. So everything which is in motion has certain speed associated with it. So when we try to talk about their motion, or when we try to describe their motion, we try to describe how fast the object is moving, and that is where we talk about speed. I hope you found this video useful. If you have any feedback, do let us know in the comment section. In the next video, we are going to discuss some very important, very interesting questions based on motion and time. So be with us.